Right, at that stage, we are ready to draw our lines of best fit. And our lines of best fit should be straight line relationships. You'll notice that there is no way that that graph is going through 0. So again, we do not put our line or any lines of best fit through 0. Okay, we don't force the line through 0. So what we're doing here is we're actually going to do 2 lines of best fit. We're going to do a steepest and a shallowest line. I will do one in black and one in blue, so it's hopefully a little bit more visible. Because the data points are so close together, it's going to be quite hard to see the difference between our 2 lines of best fit. Okay? Now, in an experimental sense, that means that that's a good thing because it means that our results are really close together. It means that we're very certain about all of the different times for each change in height, or for each square root change in height. But when it comes to us getting information from our lines of best fit, it's going to make our job a little bit harder. So my shallowest line of best fit is going to start from as high as possible at the bottom end and go to as low as possible at the top end, hopefully intersecting most of those data points along the way. So as high as possible there and as low as possible at the top end. And that looks like it does fit those other points reasonably well. And I might exaggerate it slightly just so it's slightly more visible for you guys. So I'm going to do a solid black line for that one. So that's my shallowest line of best fit. And I might just note down on here that the black equals the shallowest. And I'm going to use blue for my steepest line of best fit. And so the steep one, if you think about a hill, it's going to start off low down and it's going to go to as high up as possible. So we're starting low down from here and we're going to high up over at this end. And again, I might just exaggerate it a little bit to make it more visible for you guys. So you can see that they do separate out. They are visibly separate lines here and here and down here, but I understand that they are very close in terms of gradient. Okay, so at this stage, we are nearly ready to work out what our final equation is for the relationship between these 2 variables. We need to work out the gradient of each line, and then we're going to use that information to form the equation. To work out the gradient, you may remember that it's rise over run from previous years, and we're going to circle 2 places on the line. We're not using data points because you can see these data points don't actually lie on the line. So we're using places on the line, and you want to pick places where the line cuts across a junction on the grid lines to make it as easy as possible for you to read off the values from the axis. So I'm not sure how well the video will be able to show this, but I reckon on the blue line, just here it crosses 2 major grid lines, which makes it really easy for me to see that it's 45 on time and it is 4.2 on our square root change in height. Yep. Then we're going to go down to this end, and where's good? I think this point down here, it's just a little bit higher than the grid lines I would like, but I think it'll work out just fine. So I'm going to circle that point there, and I can see from that that the change in height value we're going to be using is, it's going to be 1, then there's 1.2 there, and remembering that each little box I've worked out as being 0.04 means that it is 1.24 if it was here, 1.28 if it was here, so it's going to be 1.32 on here. And I might just write that in, so 1.32, And then along here, I've decided that that was right on the major grid line of 4.2. Okay. Now, I do recommend using construction lines to help you read those off. So I'm just going to show you what that looks like. Dotted lines that go down to the axis, and that allows you to just identify the place on the axis really clearly. I'll do the same coming along this way. I probably don't need to do it so much with this point because it's right on a major grid line. But so we can hopefully see there that it intersects right at 45. And then for this lower one, okay, and I reckon that's probably 8 on the time axis. How did we, because I chose that point. I chose points that were far apart. And that lined up with the grid lines from the graph paper to make it easier for me to read the values on here, okay? If I chose 2 places that were close together, then it would be harder for me to be certain about the relationship, about the particular values as I go down to read off the axis. By making them far apart, my gradient is more likely to be correct. Jose?
There are 2 lines in there. I noticed that both lines are both points of gradient are in the same line. Does it have to be in the same line, or it can be on different line? Because there is a steeper and shallow line.
Yeah, so I'm going to do the same thing now for the black line, which was the shallowest line. So I'm going to work out 2 different gradients.
Do we have to do that as well?
Yeah, absolutely. Okay. So shall we work out the gradient now, or shall I identify the points on the black line I'm going to use first? Yep. Okay, so I'll take my black pen and find a couple of good points on here. I reckon that point there, and Biniam, this sort of relates to what you were asking about. So I picked that point there because it lines up, it cuts across the junction between the grid lines. And then up here, remembering that I'm trying to get as far out as possible if I can. Yeah. I could almost use that point right at the end there, which I think I'm going to do. Okay. And so if I come down, I know that that's going to be 4.4. Okay. And I can draw my construction lines just to reinforce that. So I'm using dotted lines that go down to the axis. Over here, dotted lines that go down to the axis, and I can see that we're on, what was that, 1.4? Well, if I go there, it's 1.6, and it's 0.04 less than that, so that's going to be 1.56. And then I'm coming along here. Alright, and that one's nice and easy, that's 12. And coming along here, and I think 46 is reasonable there. Okay, so you can see what it looks like once we've got 2 lines of best fit, 2 construction lines, and our next stage is to work out the gradient. Right? So this shows up a little bit more easily on the video. I'm going to write down the values that we're using, and then I'll turn over and do the working on there. So we've got, for our blue line, our rise goes from 8 to 45, So for the steep line, okay, our y, or change in y value, rise, equals 8 to 45, which equals, that's like saying 45 minus 8, which is of course 37. For our run for the blue line, we're going from 1.32 to 4.2. So you can see that on the scale here. We've got 1.32 to 4.2, and so our run is, what did I say? 1.32 to 4.2. All right, and what does that equal? Well, that's the same as 4.2 minus 1.32. We're working out the difference there, and that's going to be, what, just shy of 3, so maybe 2.88. And my glamorous assistant Johannes is working that out on the calculator as we speak. 4.2 minus 1.32. 2.88. Okay. All right. Well, now that we've got the rise and the run, the gradient of any straight line is given by rise divided by run. Okay. That's also the same as saying our change in the y value divided by the change in the x value. I don't really like referring to y and x because there's a risk that you might then refer to y instead of time. Okay, so that's really our change in time divided by our change in the square root of the change in height. Okay. Look, that's not really important. What's important is the rise and the run, and if you guys can remember that, then you're all good. So our rise over run, our rise was 37 and our run was 2.88, and so our gradient comes out to be, glamorous assistant Johannes, hard at work again, 12.84. Well, it comes up 847, so I'm going to write that as 12.85. Okay. All right, we're going to do the same thing now for the black line. So that was our shallowest line, and for the shallow line we're going, our rise is 12 to 46, what did you say, Jose? No. Okay, so we've got 34, I think, and then our run is, what have we got there? Was it 4.4 minus 1.56, which is going to come out as 2.84, right? And we know that our gradient, and I'm showing this working because I want you to show the working as well, rise over run, which equals 34 divided by 2.84, which comes out to be 31.16. Okay? So our shallowest is 31.16. Our steepest, oh, hang on. Johannes, sorry, I think you've done minus rather than divide there. Yeah, I said glamorous, not clever. All right. Much better. And I should have spotted that, so I can lump myself in that same insult. All right. 11.97. That's looking much better, isn't it? Okay. And we would expect those to be relatively similar. So we've got 12.85 from our steepest. So the steepest gradient is 12.85, and shallowest is 11.97. What we do with that then is we work out the average of those two for our equation. So we're going to work out the average, and so we're going to do average gradient is 12.85 plus 11.97 divided by 2. And that comes out to 12.41. Okay? Common sense check here. It's got to lie somewhere between these two values, and if it doesn't, then you've made a mistake on the calculator. Okay, and the last thing we need from the gradient is our uncertainty in the gradient. And so our uncertainty in the gradient is half of the range. So what we say is that we think the gradient is about 12.41, but we know that it could be a little bit higher or a little bit lower than that. And we need to know how much higher, how much lower. So our uncertainty in the gradient is the range, and we work out the range by taking the 12.85 minus 11.97, and it's half of that value. So our uncertainty is 12.85 minus 11.97, which is going to give us 0.88, and then we are going to divide that by 2. So it's 0.88 divided by 2, which should be 0.44. Okay. And what we do then is we can say that the gradient is 12.41 plus or minus 0.44. And what do we want to do with that? Technically, an uncertainty should only ever be one significant figure. And so it's going to be 4. Well done if you spotted that. So this becomes 0.4. Okay? There's some argument for saying, well, you should round up because it's an uncertainty, but I'm happy with you rounding to the nearest value for that. And then the 12.41 is reported to the same level of significance as the 0.4, and so our gradient, our final value for gradient that we're going to use is 12.4 plus or minus 0.4. And that means that we're pretty sure our real value for gradient is within 12.4 plus 0.4, which is 12.8, or as low as 12.4 minus 0.4, which is 12. Okay? Any questions?